the introduction. Hello everyone. So let me first thank the organizers for a great workshop and for inviting me. I was working in Paris until recently, and I recently moved to the Swiss Data Science Center. Since many of you probably don't know about it, I'll try to say a few words at the end of my talk. But first, I would like to tell you about an algorithm that we worked on with my PhD student, Shel Suhu, to have fast convergence for learning conditional random fields. So this is joint work with Shel, who is now finishing his PhD. He's been working on conditional random fields, and now he's working on deep learning and Bayesian methods for deep learning, and he's looking for a postdoc. So if anybody is looking for a postdoc, please talk to him. He's here. All right, so what is the outline of my talk? I'll first start by motivations, and then I cast a problem, and as you'll see, we'll have to reformulate the problem several times before we can get from it an efficient formulation or formulation that is amenable to an efficient formulation. Then I'll propose an algorithm which basically will be fairly natural given all the preliminary discussion. If I have time, I'll state convergence results and present experiments and conclude. Okay, so 6 or 7 years ago, this kind of problem that I'm showing here, that is the problem of scene semantic segmentation, would have been the best example of a case where conditional random fields would be the method of choice. Since then, essentially, deep learning has somehow swept away part of these techniques. The reason why I'm showing this image is because today I'm mostly concerned about optimization, and I would like to have a clear explanation or presentation of the problem that I would like to work on. But then you could tell me, okay, so today to do semantic segmentization, we don't use conditional random fields anymore, so why is it relevant to still talk about them? So conditional random fields might not be still that relevant for this particular example that I'm more using as a sort of way to explain what I want to do. But one of the advantage, in particular, people have worked on hybrids between conditional random fields and convolutional neural network, adding layers that perform the inference that conditional random fields do or approximate this conditional inference. But still, so when you learn with convolutional neural networks, you need to have large amounts of data, and you don't really have a good way to encode structural priors that you have on the structure of the output that you'd like to predict. So let me just give you two examples. In work that we did with colleagues in the Imagine team a couple of years ago, we worked on facade segmentation, and we could include priors that basically encode that usually windows are aligned horizontally and vertically, and that elements of the architecture have a certain structure. And this was expertise that was encoded in the model. The model was essentially very close to being a Markov random field, and we wouldn't have been able to put that easily this a priori in a neural network. And then, if you work, for example, in computational biology, sometimes you like to make predictions, structured output predictions, where you predict labels of gene, for example, in the gene ontology. And there again, you've got parts of the ontology that places hard constraint on the set of labels that are possible. And if you don't take that into account, your predictions might not be satisfactory. And that again is something which is not so easy to encode in a convolutional neural network. Okay? But for today, the example that I'm showing here is more to describe the problem that I would like to study, which is more an optimization problem. So the goal here is to take an image and make at each pixel classification to assign this pixel to one of a fixed number of classes. Typically here, you'd like to classify a pixel as being part of roads, sidewalk, humans, trees, and so on. So I think there are 8 class labels here. So if you were to solve the classification problem point-wise, this would just be like pixel-wise. It would just be a multi-class classification problem that you could solve, for example, like logistic regression. But obviously, there are spatial dependencies here that you would like to be able to take into account and in particular learn. So we're going to view this image as being a grid with interactions between adjacent pixels, that is, interactions that are supported by edges in that grid. The question is, I mean, these problems are typically quite difficult, learning conditional random fields. I mean, I'll present the structure of the optimization problem in a minute. But you know, we've seen recently the development of a number of fast algorithms for the case where the objective function is a sum of a large number of functions, which some of you may know, like such as SAGA, SVRG, and SDCA, which are stochastic algorithms with variance reduction. And so what's the idea of these algorithms is you assume that you have an optimization problem of the kind that I've put on this slide, where you're minimizing a function plus a regularizer. The regularizer is not necessary for all of the methods that I'll be mentioning. But the key point is that f here is a sum of a large number of functions. So you want to think of the number of functions here as either being indexed by the number of points in your data set, or for the application that I presented, being the sum over functions that are indexed by the pixels in the image, right? So you have like millions of functions in the sum. And each of the functions typically is of the form of a sort of loss function that's applied to the dot product between a parameter vector and a feature vector at that position. So I just wrote there the different updates for different algorithms that use variance reduction. All of these algorithms are of the style of doing gradient descent, except that you don't recompute the full gradient of the objective at each iteration, but you actually just pick one of the functions at random and you build from it an approximation of the running gradient. And I'm not going to go into the detail, but the idea is that all of these methods have you see that you pick a pixel at random for a case or a point at random, and then you use a stochastic gradient, but the stochastic gradient is corrected by a term which has the property that by adding these terms, the variance of the overall estimate of the gradient tends to 0 as you're converging. And so most of these methods have this form, but there is a sort of a outlier in a way, which is stochastic dual coordinate descent. In fact, stochastic dual coordinate descent can also be written with updates in the primal of this form, but it's an algorithm that is naturally described in the dual. And so to describe the algorithm, you have to write the dual of, a dual of the primal problem that I wrote at the top. And so using duality, here using either Lagrangian duality or Frenchel duality, you can get that the dual problem has this form, and here we have what is called dual decomposition. That is that we have a sum of a large number of functions, each associated with one of the pixels or point that I presented before, and a function of a single dual variable alpha s. And so a very natural algorithm consists in doing stochastic dual coordinate descent, which is to sample one of these variables and update it with a gradient step and then a proximal step with the proximal operator of the function f star. I'm not going to get into the detail because this doesn't matter too much for what I'm going to be talking about. My main point here is that this is an algorithm that runs in the dual, and it has the same property as these other algorithms which I have listed here, which is that once you compute from these dual variables corresponding primal updates, then you have an algorithm that is also an algorithm that you can interpret as an algorithm which has stochastic updates with variance reduction. And the point is that these algorithms have been studied a lot recently, and in particular, so they have very good rates of convergence. So here I've put a table where the first 3 lines correspond to methods that are applicable to general functions f, and the 2 last line are algorithms that are applicable to functions that are sums of large number of functions, and essentially the corresponding convergence rates that have been established for these different methods. And so what you see is that if you use stochastic gradient descent, then you have a convergence which is slow, which depends in 1 over epsilon, where epsilon is the precision that you want to obtain. And then if you use either of these gradient descent or accelerated gradient descent, then you've got the number of the condition number of the problem is multiplied by the number of data. Whereas when you use these variance reduction methods, then somehow the number of data points or the number of pixels and the condition number appears in the additive way, and this leads to very fast algorithms. So exploiting sum structure is something that is established by all this by the theory behind this as something that yields fast algorithm. And so we can apply that to problems which are of this form. So if, again, you think of the problem of making predictions at each pixels independently in the image that I've shown before, then this is essentially applying a model that learns something like multi-class logistic regression. And so if each of these graphs here represent one of my pixels, then I have a graphical model where everything that happens at each pixel is independent, and which yields a sum of functions that I can therefore optimize with the algorithms that I have mentioned. So what I want to think about is what happens now if we would like to take into account the dependencies between the neighboring pixels. That is, if now I add connections between the output variables y, I add a dependent structure, which can be more complicated than what I have represented there. What happens, right? So all of a sudden, your objective that was a sum of independent functions are all coupled together and become a big function where everything is lumped together. So, however, it seems that in this large function, each of the edges here appears makes a separate contribution, and somehow we'd like to be able to leverage these separate contributions to have an algorithm that somehow is able to optimize this faster. Okay, so now I'm going to try to formalize the problem and therefore write for our conditional random field what is the log likelihood of our problem and a formulation that we would like to optimize. So I'm going to assume an input image x, and at each pixel a feature vector phi s of x. I'm going to encode the class that you would like to predict at each pixel with an indicator vector ys, and ys is a vector which is a binary vector with one of the elements in that vector which is equal to 1, corresponding to the class that is the right one. So ysk is equal to 1 if and only if the class of pixel s is k. So then if we want to have a model for each to predict each pixel independently, as I said, we can use multi-class logistic regression. And so we have a conditional probability of ys given x, which can be written in this form. So I'm not writing the full probability. I wrote proportional to exponential and then what's inside the exponential. And of course, we would need to include a normalization constant there, right? But for the logistic regression, the normalization constant is not too hard to compute. Now, if we would like to predict the whole image at once, we would like to have a model of the probability for y1 up to ys, where capital S now is the number of pixels in my image given x. And so what I'll have is essentially here 2 terms. One term, which is essentially the counterpart of the term that I had before, that is a contribution of what I will call unary terms. So this is a score that's built from the feature vector at pixel s, and then essentially I've got a different score for each possible class k, so this is the expression of the likelihood for this part. And then I'm going to have a second energy term, which corresponds to the interactions between adjacent pixels. And which is going to attribute a score essentially w tau 2 KL for the fact of having two neighboring pixels, S and T, in which the pixel S has the class K and the pixel T has the class L. Okay? So the reason why I have introduced w tau 1 and w tau 2 is because essentially I'm going to distinguish two types of potentials. Tau 1 refers to the potentials of type 1 here, which are unary potentials, and tau 2 refers to the binary potential, which are type 2. But then you could imagine having different binary potentials that are of different types, and so on, right? So this could be extended beyond this framework. And in particular, when we work with conditional random fields, we can have interactions of order 3, 4, and so on. But here I will limit myself to interaction of order 1 and 2. So the work that I'm presenting can be generalized to higher order without major difficulty. So then the idea is I will try to rewrite, so that's the likelihood for a single image, the log likelihood for the likelihood for a single image, except that again I wrote proportional 2 because I didn't write the normalizer, which is a log partition function, which now is complicated to compute. So I would like to reformulate the problem and rewrite it now when I have actual data. But this is the part which is a bit technical. So let me first tell you like a trick that I'm going to use in the calculation that I do. So hopefully by presenting the trick separately, it's slightly easier. So whenever you have a model that you can write as an exponential family, the negative log probability, which in the case of a conditional model, is something that I can write as the dot product of the canonical parameter and the vector of sufficient statistics, and then plus the log partition function, which depends, of course, on the output x0 and is a function of the parameter w. And what I would like just to show is that, in fact, we're going to be able to rewrite this negative log likelihood as the log partition of something. Okay, so this is something that, once you have seen it, it's fairly natural, but if you have not seen it, then it seems surprising because it seems that there is a term that's missing. So the log partition function, by definition, is the logarithm of the sum over all possible values of y, which can be here, I wrote this sum sign in red because this sum can be over an exponential number of terms of the exponential of, again, the score. And now you note that, in fact, the term that's on the left, I can write this as the logarithm of the exponential of itself, and therefore I can push it inside of the sum. And so I can rewrite this exact same expression as now the logarithm of the sum over y of the exponential of w dot product with a difference, which is the difference between the score at a certain y that I'm summing over and yo, which is the y that I'm observing. Right? So by the way, I forgot to say, but the fact that I have an xo and a yo correspond to the fact that x is observed and y is observed. So I added these two for clarity. Okay, and now if you look at what you have in the inside of the sum, basically this is something of the form log sum x. So then we can expand. If we have a graphical model, then this dot product is actually a sum over a certain set of cliques. So here, in our case, the cliques are going to be just the nodes and the edges. Okay, so it's going to be a sum over nodes of dot products of this form plus sum over edges of dot product of these forms. And what are these dot products? Well, it's going to be a piece of the parameter vector dot product with a piece of the vector of sufficient statistic. Okay, and so we can rewrite this in that form where I have defined theta to be actually equal to this difference of, theta to be the dot product between my parameter vector and this dot product. And so the idea is that now this is exactly, this is of the form log sum x. So you can view this as actually being the log partition function of some parameter theta. Okay? So the whole point of this slide is to see that we can rewrite the negative log likelihood as the evaluation of the log partition function at a certain point, which depends on the data. and which is a sum over, which is, involves inside a sum over all the variables y that are possible, so an exponential sum. So, okay, so what happens if we now take again our model and we try to rewrite it in this form? So, again, this is the form of our model, and to simplify what I'm writing, I can abstract things out a bit, and I can in particular write that here what I have is in fact a dot product between a vector w tau1 and a feature vector which is bigger, which involves both the labels at node S and the feature vector at node S. And then similarly here, I can abstract this out and write this as a dot product between a vector w tau2 and a feature vector that possibly depends on the labels at the edge and x0. So here x0 doesn't appear, but an extension could include it. Now, once I have done that, then I can group all of this together and say that this is just a sum, because so this is a sum over nodes that are cliques of size 1 and edges that are cliques of size 2. So this is a sum over all the cliques in the graph, right? C, the set of cliques, is the union of the set of nodes and the set of edges of the dot product between w tau c and my feature vector. And so far, I've written the conditional probability with proportional to something, and now I would like to actually include the log partition function. So here, this is the log partition function, and the definition of the log partition function is that this is the sum, which is a combinatorial sum, over all the possible values of the first pixel, the second pixel, the third pixel, and so on. So if you've got millions of pixels that take 8 classes, it's 8 to the power 1 million terms that you have in this sum, so it's a big sum. And the log partition function is of this form. Now, if we use exactly the trick that I presented in the previous slide, then we can rewrite the log likelihood as being the log partition function of this term that involves a difference. And then by massaging the different terms, we can introduce a design matrix which encodes all the information which is relevant for the prediction and encodes all the data. Which is this matrix psi c, and we can essentially write our objective as being a function f of this matrix psi multiplied by w, where f of theta now is the kind of log partition function that I have introduced before. Okay, so what we have is, instead of having for the case where the graph is disconnected a sum of log likelihood of logistic regression, now we've got the log partition function applied to some transformation, some linear image of W by a matrix that depends on the data. Okay, so then the idea is to try and exploit the structure of this object to try and again have fast algorithms. So how do we do that? Okay, so I rewrote here, I guess maybe this is superfluous at this point, but I rewrote here the equivalent of exactly the formulation that I just derived for the case where we only have unary potentials where there is no connection. So in that case, is this? Sorry, this is the next slide. So no. So what we would like to consider is instead of maximizing the log likelihood, we'd like to consider regularized formulation in which we minimize the negative log likelihood plus a regularization term with the functions that I've now introduced, f, which is a log partition function. The major problem here is that, and so I don't have time to make a review of the literature on learning graphical models or conditional random field, but essentially the usual strategy to optimize this time of objective is to try and compute the gradient of the function f. And the problem is the gradient of the function f is going to involve the difference of the vector of sufficient statistic and the expected vector of sufficient statistics under the model, which requires to do inference in the graphical model, which is NP hard. Okay? And so people have considered ways of doing approximate inference that involves using Markov chain Monte Carlo method, but this is still relatively slow. Then people have considered the possibility of approximating this gradient using variational method, but then at each iteration you still have to solve an entire optimization problem. So essentially, there are a number of difficulties to overcome, and so we're not the first one to try and address these difficulties, but we need to try and find a way to avoid all these difficulties. Okay, so I'm skipping the slide that discusses again the disconnected case. The disconnected case is a case on which we can apply these algorithms such as SAGA, SVRG, SDCA, and so on. So we'd like to be able to apply the same kind of algorithm. So one thing that we can try and leverage is the representation of the log partition function in the dual. So the idea is that this log partition function can be written as using its Fenchel conjugate. So the Fenchel conjugate of the log partition function is the Shannon entropy. And in particular, we can write the log partition function as the maximization over this new variable mu of the dot product between mu and theta plus the entropy of mu with a constraint set on mu, which is this set M, which is what people call the marginal polytope. So the mu here is actually the collection of what people call realizable moments. So it's possible, so mu is composed of a lot of small vectors that are mu c. So mu c is indexed by the cliques, which means it's the vectors either mu s, where s is a node, in which case it's a distribution of probability over the possible classes at node s, or the clique is an edge, so it's mu st, and then it's a probability distribution, a joint probability distribution over the possible classes that are assigned to node s and node t at the same time. So in the set of the moments that are possible, by which I mean the set of moments which are actually associated with a certain random variable y, is called the marginal polytope. Unfortunately, this object is fairly complex. And so as I said, H Shannon is the Shannon entropy. And so if we use these elements, then we can, if the primal problem that we wanted to optimize was this one, we can actually write a dual optimization problem which corresponds to this primal problem, which would amount to maximize d sharp of mu with respect to mu. And so this dual optimization problem, which would be equivalent to the primal problem, unfortunately involves two terms, namely the Shannon entropy and the marginal polytope, which are NP hard to compute. So the marginal polytope has an exponential number of constraints, and Shannon entropy is intractable to write also because, you know, of the similar reasons. So what can we do? So a classical approach to overcome this problem is to actually consider relaxation of the polytope and to have also a surrogate to replace the Shannon entropy by a surrogate. So in particular, what people have proposed is to replace the marginal polytope by what is called the local polytope. And the local polytope is defined as follows. So I'll try to describe how we construct the local polytope. So the first thing that we'll do is we'll require that for the dual variable mu, for each mu s, which is again a probability distribution over the possible classes of ys, has to be a valid probability distribution. Namely, the entries have to be positive and it has to sum to 1. Then we have a similar constraint for the moment on the pairs, namely it has to be positive and sum to 1. And then with these two, I mean, basically those are independent constraints that you place on each clique. And the collection of all these independent constraints I will call the independent polytope, and I will denote that this I. Now, what is the local polytope? Well, the local polytope is the set of moments mu, which are in the independent polytope, and which in addition satisfies some what people call marginalization consistency. And what is the marginalization consistency? Well, it just says that if you take the probability distribution for a pair ST and you marginalize out the variable YT, then you should get a vector that is a vector of probability on YS, which is the same as mu S that you have defined for the corresponding node. Okay, so we're basically requiring that the distribution that you've placed on pairs marginalizes to the distribution that you've placed on single nodes. Now note that therefore the marginal polytope, the local polytope is the intersection of I, which is a Cartesian product of sets, and a big linear constraint, which is the collection of all the linear constraints that I've put in pink, right? So then you can construct a matrix A, which actually encodes all these linear constraints. Okay, so I'm going to be optimizing over this set L, which is the intersection of I and the pink set, which is a set of linear constraints. Okay, then we need to essentially come up with surrogates for the entropy. And let me be quick on this. So there is a long history of surrogates to introduce, but essentially the discussion is a bit complicated of like which one are suitable for our case or not. So it turns out that it's possible to constrain reasonable surrogate of the entropy that are actually sums of functions on each of the cliques. So this is what we will consider, where each function is smooth and convex, and where the overall surrogate is strongly convex on the local polytope. So there are several ways of doing that, either using the Gini entropy locally or using what's called the oriented tree-weighted entropy, and I don't have time to enter in the details. So essentially what we've done is we've written the dual problem. In the dual problem, we have done the classical relaxation, which consists in like replacing the marginal polytope and the Shannon entropy by these counterparts that are on the right. And so we are relaxing our dual problem to the following formulation, which means now that if I actually exploit the structure of the different functions that I have, n sets that I have introduced, I can rewrite my dual optimization problem as the sum over these function fc star that are supported on cliques, right, where fc star is actually the combination of the local entropy and the local set of constraints, then minus a term which is actually the regularization here, and then minus this big linear constraint. So then what you see very quickly is that if I didn't have this pink term, then I would have exactly the type of formulation which has dual decomposition and where I could use stochastic dual coordinate descent. So at this point, to be able to apply stochastic dual coordinate descent to this type of formulation, I need to find a way to get rid of the pink term. So how can I do that? Well, a natural thing to do when you have a linear constraint is to relax it. And a clean way of doing that in optimization is to actually introduce an augmented Lagrangian function. And so this is exactly what I'm going to do. So I'm going to replace this constraint by a linear term here where C is a Lagrange multiplier and a quadratic term here that corresponds to the augmentation. Okay. Now you see that I can basically view these three terms all together as some regularization, and now this formulation is amenable to stochastic dual coordinate descent. Okay. So in particular, I can again now in this case use duality because the formulation that I've written is the maximization of the original prob of D with respect to mu, but now I've added a variable xi. So in fact, it's the maximization with respect to mu of the minimization with respect to xi, but strong duality holds, so I can actually exchange the order of minimization and maximization. And the problem that I'm trying to solve is actually equivalent to the minimization with respect to xi of this objective dxi, where now dxi is itself formulated as maximization with respect to mu. Okay, so what is the algorithm that we will use? So it turns out that when you use an augmented Lagrangian method, the gradient with respect to the variable xi is very simple because it's actually something of the form A mu xi, where mu xi is the solution of the optimization problem in xi. And so if we want to do gradient descent on the function small d, then we just need to solve the minimization problem in mu and then do an update on xi, which is going to be xi of this form, ct plus 1 equals ct minus 1 over L a times mu. Except that you don't want to be solving the maximization problem in mu exactly at each iteration. So what we basically are going to do is to do a couple of passes of updates on mu, not completely solve the optimization problem, but just make a bit of improvement, have an approximate gradient for xi, and iterate. Okay, so this is basically the algorithm that's described there. So you fix a value of xi, you do a couple of passes, a few passes of stochastic dual coordinate ascent, for example, or any other linearly convergent algorithm on mu, and then you do an update on xi. So I realize I'm a bit running out of time, so I'm not going to go into the detail of the technical lemma, but essentially what we show is that we introduce the different suboptimality gaps, and we show that if the algorithm that you use to optimize over mu is linearly convergent, then you need to do a fixed amount of work with this algorithm, and then use the corresponding mu to do an approximate gradient descent step on xi, and that this is sufficient for to obtain linear convergence in the overall problem. Okay, and then how much work you have to do in each inner loop is actually characterized by this lemma, but I don't have time to go into the detail. Okay, so essentially what we show is summarized here, which is that the two suboptimality gaps converge linearly almost surely, that the residuals also converge linearly, and we have, and I apologize for going a bit fast on this, but it would just take me way too much time to describe them in detail, but we can actually also show, which is what we care about, that not only we have solved the dual problem in mu with a linearly convergent algorithm, but we also have a linearly convergent algorithm in the primal. That is, the parameter w that we wanted to learn is linearly convergent. So there's a long history of related work, and essentially, so the idea is that people have first considered saddle point formulation, where I mean you need to basically solve a sequence of problems to do the learning, and there's a sequence of work that basically leads to this possibility of considering to work at the clique level, but essentially the main contribution of our work is that nobody had actually made the connection with stochastic dual coordinate ascent and proved the kind of linear convergence rate that we have proved. So let me just show you a couple of simulation. I'm just going to compare with what is really close to the state of the art. I mean, there are something like, probably like 20 different methods that you would have to consider to do an exhaustive comparison. But I'm basically comparing with only a few methods, because essentially the first method that I'm comparing to, which is soft block coordinate Frank-Wolf, is from a paper of Ofer Meshi, Natiz Rebro, and Tamir Hazan, in which they have done, maybe not in that paper, but in a previous paper, there's an extensive comparison with the related literature, and this is significantly, their algorithm is significantly faster than the related work. And so, so what they do is they have a formulation which is similar to ours, but then they just use a penalty method. They don't use alternating, like they don't include a Lagrangian, or they set the Lagrangian to 0. And then we compare with a variant, which is called soft dual coordinate ascent, which is essentially a variant of our algorithm, but where we don't update the Lagrangian. Then there is this GDMM, which is slightly more recent than Meshi, and which is a greedy algorithm, which essentially exploits a bit the same kind of structure as our algorithm, but somehow it's greedy, it's not stochastic. And then our algorithm, which is called IDAL. And so I'll show you like comparisons on first a synthetic data set, and then a problem with where you want to do segmentation of images. And so, okay, so what are all of these plots? So at the top left, you've got the convergence in terms of duality gap. So I mean, the prior literature doesn't actually represent convergence in terms of duality gap, because the duality gap are not so simple to compute. And then the gap on marginalization constraint, excuse me, is the gap to the satisfying the constraint. And what you see is that we're exhibiting linear convergence in both of these things. And unfortunately, so we are the orange curve, and the methods in blue and red, which are the method of Offer-Meshy and the counterpart when you use stochastic dual coordinate descent, actually converge quite quickly at the beginning, but since they don't enforce the correct constraints, because it's just a penalty method, it's an approximate, they only approximately enforce the constraint, then the duality gap cannot go to 0 and they cannot enforce the constraint. However, in terms of performance, all methods perform relatively similarly, so it's difficult to really sort of say that we do significantly better, even though in terms of test data we're slightly above the other methods in the end. Okay. And so we did also experiment on segmentation, and this is a variant of our model where in fact we remove the entropy term, and which is closer to a structure support vector machines. And in that case, it turns out that the method that does block coordinate Frank-Wolf is actually faster, but it doesn't, again, satisfy the marginalization constraint. And so, so then in terms of accuracy, then again, the question is a bit delicate because we seem to have the orange and red curves correspond to the two variants of what we propose, seem to be going up a bit faster. The green method, which is the greedy algorithm, doesn't seem to be very stable. But well, this is essentially not so clear from these experiments that actually trying to enforce the constraint exactly, we necessarily gain in this type of application. However, the problems in which there are constraints, linear constraints that are coupling a problem are many, and so we can apply the same kind of technique as the one that I presented to tackle these problems. Okay, so with that, I'll conclude. So essentially, I presented a way to apply stochastic dual coordinate descent to the dual of, a relaxed dual of the CRF learning problems. Essentially, our contribution allows to identify, to basically the link with SDCA and to obtain fast rates of convergence, and there are a number of open problems associated with this. Maybe if I have a couple of minutes or 1 or 2 minutes left, before taking your questions, I just would like to say a few words about the Swiss Data Science Center. So the Swiss Data Science Center is a center which is affiliated with both the EPFL and ETH Zurich. So it's affiliated to both universities and it has offices on both campuses. The academic mission of the center is to collaborate with research laboratories, currently mainly the national labs in Switzerland, but later will most likely open up to other labs to try and help these applied labs to solve the research problem that they're working on and which involves data. So we're working with people in physics, working with biomedical data, in climate, in cosmology, in humanities, in economics, lots of different application domains. So some of the images that I'm showing you are, if you are interested, you can have a look at the website of the Swiss Data Science Center and get detailed information about the different projects. This is only 8 projects. This is another set of 8. I think at this point we have 24 on the website and we have 8 new projects which are starting this year. The 8 new projects are even more exciting than many of the projects that are listed here. There's a project of collaborating with the CERN to actually do control over the accelerator, collaboration with people who work on the winds in the stratosphere. collaboration with people who work on predicting avalanche. I mean, lots of interesting things. And so, okay, so we're based on 2 sites. The way the center works is that it's formed of different teams. There is one team, which is the core data science team, which counts people who mainly have expertise in machine learning. This team is led by Fernando Perez-Cruz, who is based in Zurich, and I'm co-leading the team being based in Lausanne. We have 11 data scientists at the postdoc level who are working on a number of the projects that I have presented, and we would like to be hiring more people because we have a lot of projects. And we have a few data scientists that are the master or PhD level. There's another team in the center who actually develops a platform to do data science, and in particular, which is an equivalent of GitHub for data analysis, if you will, to summarize it, which ambitions to basically propose a platform which makes it easier to actually track what you do when you do large-scale experiments on a lot of data. And we have a team of 9 software and system engineers who work on that, and those are seasoned people. More than half of them have actually a PhD in software engineering or system engineering. And we also have industry collaborations, and a few of the data scientists in the team are actually working on this. So if you would like to have more information, the website is easy. It's datascience.ch. And with that, I will thank you for your attention.
Is there 1 or 2 quick questions in the audience? No? Okay, so I have one. Because you mentioned a relaxation of the dual problem, and then you went a bit quicker. So can you control the corresponding primal problem? Or is it far from the original? Or?
You mean going from this relaxation? You mean going to the NP-hard relaxation to the one which is not NP-hard?
Yeah.
So okay, unfortunately, the gap between these two is hard to control. I mean, like this question has been around for a while, and knowing how much you lose by doing the relaxation with a local polytope, is something that people don't know quite well. However, what we can do is that we can relate back. This dual, and once we have done the relaxation in the dual, we can construct again another primal which corresponds to this dual, and we can track the duality gap between that primal and the dual that we have introduced. Okay. So so how far we are in that respect is difficult.
Okay. Thank you. So let's thank the speaker again.